Alright guys, so in this video we are going to look at non-rigid transformations, and these are going to be basically stretches and shrinks that we see horizontally and vertically on the xy axis. And basically what we're saying is we're going to take the shape of our function and either stretch it out horizontally or shrink it down, and vertically stretch it or shrink it, depending on the transformation. So right here, first we're going to look at horizontal stretches and shrinks. And we're going to evaluate horizontal stretches and shrinks, or talk about why we get them, in the same way that we looked at why we had horizontal shifts. So we're going to find an ordered pair on our original function and talk about what x value we would need to get that same function value. So right here, first we'll talk about a horizontal stretch. And we'll say that a horizontal stretch occurs when we multiply by a number less than 1 inside the function. So if our function right here is 3x minus x cubed, where the function itself is just basically the multiplication of 3 times an input and then the subtraction of that input cubed, we would say that when we multiply our input x by 1/2, that this would be a horizontal stretch, where we would see function values stretched out horizontally on the x-axis. So what we're going to do first is just get ourselves an ordered pair for our original function here, and we're going to plug in the x value of 1. And right here, when we plug in the x value of 1, we get f of 1 as 3 times 1, and then minus 1 cubed. And right here, that's going to give us f of 1 as 2. So right here, we have that local max right there as being 1, 2. The ordered pair, 1, 2. And what we're going to do now is basically go over to our transformation with the multiplication of 1/2 inside the function and talk about what x value we would need for f. Remember, f is basically just the multiplication of 3 times an input and then the subtraction of that input cubed, right? What we would need to do to have f evaluate 1. So right here, what is the x value I would need to plug in for f to evaluate 1 and give us back that local max of 5? Well, if I think about plugging in an x value that I would multiply by 1/2 to get 1, that would have to be 2, right? So essentially right here what we're saying is that when we multiply by 1/2 inside of our function, we actually need to plug in the x value of 2 to get that same function value. So right here, for our f of 1/2 x, we get the function value of 2 at the x value of 2. And really what we're saying is we'll see that for all of these x values, right? All these x values are basically going to have to be double what the x values were for f of x in order to get the same function values. Now, what we want to take note of right here is that this function, right, is going to give the same function values no matter what, because basically right here what we're saying is that the function itself isn't going to be changed by what we're doing to x specifically, right? So when we talked about transformations at the very beginning of class, we basically said that when we're doing things to x, we get the same function values, they just happen at different places on the x-axis. And now what we're saying is those function values are stretched out when we multiply inside the function by a number less than 1, right? And what we want to think here is basically that we're slowing down the process of plugging in x values. Every x value is 1/2 of the x value that we plug in, right? So essentially what we're doing is slowing down the processing of x values by multiplying the inputs by 1/2, right? Now, when we're talking about this as a transformation, we wouldn't say that this is a horizontal shrink by 1/2, because actually we're twice the width, or we basically get the function values at twice the x value. We would say this is a horizontal stretch by a factor of the reciprocal 2, right? And basically that's because it's taking us twice as long on the x to get to those same function values, right? Now, right here, when we're looking at horizontal shrinks, it's a lot of the same logic. Right here, we say that we have a horizontal shrink when we multiply by a number greater than 1 inside the function. And again, we can sort of go through that same process. Right here, if we have our order pair 1, 2 for our original function, we want to say to ourselves, what's the x value I have to plug in order for f to evaluate 1 and give me 2? Well, right here, the x value that I have to plug in is going to be 1/2. And when I plug in the x value of 1/2, that's where I'm going to get the function value that is that local max of 2. And basically what I'm seeing is all my x values, or all my function values rather, happening much faster on the x-axis. Right? And again, right here, you almost want to think that that multiplication inside the function is affecting how quickly we can process the x values, right? If I am multiplying by 2, then the x-axis is sped up and I get my function's behavior on a much shorter interval. If I'm multiplying by a number less than 1, like 1/2, then essentially my x values are slowed down and it takes me longer on the x-axis to reach those same function values. So right here, what we want to do is talk about how we would refer to this shrink. And what we would say is that, again, this is going to be a shrink by a factor of the reciprocal, which is 1/2. And of course, that's because it's taking us half the time to get to the same function values, because all of the x values are immediately multiplied by 2. Okay, so right here we want to go ahead and talk about vertical stretches and shrinks. These are much more intuitive. Again, what we want to think is that when we plug in an x value into the equation, really that defines the y value, right? So right here, when we're looking at vertical stretches, it makes sense to think that multiplying the entire function by a number greater than 1 is going to basically give us a vertical stretch, or a stretch of all those y values. They're increasing, they're multiplied by that number. So right here, if I've got my f of x again as 3x minus x cubed, and that of course gives me a y values. When I multiply the function by 3, really I'm multiplying the y values by 3, and the y values are going to be 3 times their previous height. So right here we have the order pair, our order pair 1, 2, and in the sense right here what we're saying is that function value 2 is now going to go all the way up to 6, which is 3 times its previous value. Again, right here, this goes back to the way we started to talk about these transformations at the beginning of our lesson, where we basically said multiplying outside the function is basically going to give us the same function value, but altered by that multiplication of 3. Right? So basically, we still have that local min, right? But now that local min's y value has been altered, and it goes all the way up to 6 now, right? Okay, so right here, a vertical shrink happens when we multiply our entire function by a number less than 1. Again, if we think about the equation of the function really being the y values, we basically multiply those y values by 1/2 here. And essentially what we're seeing is all of those function values, the y values of the function, then cut in half, and we get what we call a vertical shrink. Now right here we would call the vertical stretch a stretch. We call the vertical stretch vertical stretch by a factor of 3, right? Because we have function values that are 3 times their previous value, right? And right here we would say we have a vertical shrink by a factor of 1/2, because of course our function values are half their previous value when we're just looking at f. So those are the vertical stretches and shrinks and horizontal stretches and shrinks. We're going to move on now and talk about some problems, some evaluations